Hey guys, this is Mrs. Harbin, and we are at the end of Algebra 1, Section 5. Today we are going to take a look at absolute value functions. Let's start with this as our lesson opener. Let's evaluate each absolute value function for the domain -2, -1, 0, 1, 2, and this function, f of x equals absolute value of x. We're going to make our little chart with our domain values there on the left. We'll put our function rule in the middle. Absolute value of x equals y. Remember that this is just y, so we can write y equals absolute value of x. And then let's go ahead and plug and chug. The absolute value of -2 is 2, of -1 is 1, of 0 is 0, of 1 is 1, and of 2 is 2. So on the right-hand side, I thought it was going to show it there. Let's go ahead and put our coordinates. Let's back up here. If we were to graph that then, our coordinates, our xy coordinates would be -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2, if we were to finish up that chart there. All right, what about this function? Let's go ahead and evaluate each absolute value for the domain -2, -1, 0, 1, 2. But for this time, let's use y equals absolute value of x minus 1. So when we plug those into our chart, we get the absolute value of -2, which is 2, and 2 minus 1 is 1. Make sure that you do what's inside the parentheses or the grouping symbol first. So we're going to simplify absolute value of -2, which is just 2, before we subtract the 1. The absolute value of -1 is 1, and 1 minus 1 is 0. The absolute value of 0 is 0, and 0 minus 1 is -1. The absolute value of 1 is 1, and 1 minus 1 is 0. And the absolute value of 2 is 2, and 2 minus 1 is 1. So again, if we wanted to list our xy coordinates there, I'm not going to write these out this time, but we have our xy, xy, and xy coordinates there. So we could go ahead and graph this 5 points if we were asked to graph it. All right, try this one on your own and then come back and check your work. Pause the video, see how you do. All right, when we plug this in, we're going to simplify what's inside the parentheses first. So when we plug in that -2, -2 plus 2 is 0, and the absolute value of 0 is 0. -1 plus 2 is 1, and the absolute value of 1 is 1. -0 plus 2 is 2, whose absolute value is 2. 1 plus 2 is 3, the absolute value of 3 is 3. And 2 plus 2 is 4. The absolute value is 4. So we've got a whole set of coordinates there that we could graph if we were asked. Our biblical correlation for this unit comes from Hebrews 3, 12 through 14, which says, "See to it, brothers, that none of you has a sinful, unbelieving heart that turns away from the living God, but encourage one another daily. We have come to share in the Christ if we hold firmly to the end the confidence we had at first." And this year I have watched you guys grow in confidence in so many areas, but specifically in math. You've gotten greater confidence in solving for unknown numbers, solving for variables, and showing your work, and adding and subtracting and multiplying negatives and positives. You really have grown in confidence. And I hope that I can continue to encourage to use those skills. And I hope that I also see you grow in confidence, not just in math, but in your relationships with one another and in your relationship with Christ. Our lesson objective for today is that you, the student, will represent an absolute value functions rule with a set of ordered pairs, a table, and a graph. So we're going to look only at absolute value functions, and we're going to represent it 3 different ways: ordered pairs, table, and graph. Now we've already talked about the absolute value function earlier in a previous lesson, because I did mention that absolute value stands for always a V when we're graphing that. So as we look at these graphs of absolute value functions, you're going to see this always a V shape. Don't forget that, super important. We know that the absolute value of a number, x, is defined as follows. Basically, it's the distance away from 0. Okay? It's the distance away from 0. It's x if x is greater than or equal to 0, and -x if x is less than 0. That would be the numbers, but for all of those, we would write those as the absolute value of x. It's the distance away from 0. The absolute value function is f of x is equal to absolute value of x, or y equals absolute value of x, if we write that in terms of y. Let's go ahead and try graphing this function. F of x equals absolute value of x. And we are given the domain -3, -2, -1, 0, 1, 2, and 3. We're going to go ahead and put that into our table where we have our x values on the left, our function rule in the middle, and then our ordered pairs on the right. And when we plug those in, we get the ordered pairs of -3, 3, -2, 2, 0, 0, 1, and 1. So those are the ordered pairs that we come up with. We can continue. When we plug in 2, we would get 2, 2. And when we plug in 3, we get 3, 3. Let's go ahead and graph all of these points. And here you can see all of these points on the graph. Since the domain was very specific, that we were only to use these 7 values, we do not connect the dots. We don't want to include 1/2 or 1.5 or any of these other values here that would be included if we drew a line. Because they gave us specific values, we're only going to graph or plot the specific points. If no specific domain were given, if we got to choose our own x's, then we would connect the dots and we would extend the arrow here to show that any x values could be used. Please note, there is a little notice here that this point right here is called the vertex. So pay attention to where the vertex is. That's going to be that point on the absolute value graph at the bottom of the V for vertex. Now this graph is called the basic absolute value function. It's also called a parent function. It is the absolute value parent function. This is the graph of f of x equals the absolute value of x. Without any numbers or anything else, no plus ones, no minus fours, just a plain basic parent absolute value function. Let's talk a little bit about translations. When a basic graph or parent function is moved up or down, left or right, this movement is called a translation of the graph. The following examples are going to show some translations of our absolute value parent function. Let's graph f of x equals absolute value of x plus 4 for all real numbers. So you can see we have our parent function here, but we have also added this translation of plus 4. Now, if you had to take a guess, what would you guess that plus 4 is going to do? You might say it's going to move it 4 up, or you might say it's going to move it 4 to the right. Let's see what we can come up with. First, let's make a table. We've got our x's on the left, our function in the middle, and then our ordered pair on the right. It did not give us a domain, so we get to choose our own x values here. So we'll pick some negative and some positive. We'll plug those into our function rule. And we get these ordered pairs, -3, 7, -1, 5, 0, 4, and 2, 6. Let's go ahead, and you can see our parent function is right here in green, and the red function is the one that we just put into our table. And as you can see, what that plus 4 did was it actually moved our whole function up 4. So previously our vertex was at 0, 0, and now our vertex is at 0, 4. Move the vertex up 4. In general, the graph of y equals absolute value of x minus h, where h is a number, plus k, again, k is a number, they're positive constants, is a result of translating the graph of the basic absolute value function right h units and up by k units. Now that may seem a little wordy, so here's a little shortcut to help you remember this. H moves your function horizontally, and k moves your function vertically. H stands for a horizontal translation, left and right, and k stands for vertical, up and down. Learn this now. It's valuable in the future, not just for absolute value functions, but for any translations. All right, so now that we know that H is a horizontal translation and K is a vertical translation, let's go ahead and look at another example. We're going to graph f of x equals absolute value of x plus 3. If you remember, we just said that x minus h, that's our horizontal translation, plus k, that's our vertical translation. And you can see we've got a 3 in here. So this is going to be a horizontal translation. So our graph is going to move 3 units either to the left or to the right. Okay, in order to determine that, we're going to see what our x is actually equal to. So x plus 3 equals 0. And we solve for x, we get x equals -3. This tells us that there's a horizontal translation of 3 units to the left, not to the right. You might see that positive sign and think that's to the right. But remember, our formula was x minus h. So this is not x plus 3. This is really x minus negative 3. So we're going to move that 3 units to the left. Okay, without graphing that, without making a table, let's go back and do a quick sketch. Okay, if this is our parent function here, then this graph is going to look 1, 2, 3, something like this. 3 units to the left here, and 3 units to the left here. Okay, it just takes that absolute value function, that entire function, and moves it to the left 3. What about when we have 2 numbers? Absolute value of x minus 2 plus 1. Well, we know that's our h. So this graph is translated 2 units to the right. Remember, we're looking at this number here. If we were to solve that for x minus 2 equals 0. So x equals 2. That tells us it's 2 units to the right relative to the parent function. And this 1 on the outside is telling us that we need to move that graph 1 unit horizontal, or vertically, 1 unit up. It's translated 1 unit up. So if we were to graph that, again, here's our parent function of the absolute value function, and this is just a rough sketch. We're going to move it 2 units to the right and 1 unit up. So this is now our new vertex, and this is our new function. The vertex is at 2, 1. So we can look at these points here, and then we can tell the translation. We can also tell where the vertex is. And when you have just the absolute value of x, you basically have x minus 0 plus 0. So our vertex there is at 0, 0. So this form gives us the vertex, and it also tells us the translation. It's also a good idea to evaluate several ordered pairs and make sure that the points are on the graph. So that's a way that you can check your work after you've graphed it. Pick a few ordered pairs and see if they actually are on the graph that you've graphed. If we were to graph that and not just sketch it, we would see that 0, 3 and 5, 4 are on this graph like they should be. Today we represented an absolute value functions rule with a set of ordered pairs, a table, and a graph. Remember, if the domain is given to you, let's say they give you a domain and they give you, negative 3, negative 2, negative 1, 0, 1, and 2, you're only going to graph those specific points. They only want you to show those domain values. If, however, you're just given a function rule and you get to choose your own x values there, and you do that in a table, then when you graph that, you are going to connect the dots because you want to show that any x values will work, that your domain is all real numbers. Any x values will work. So don't forget those 2 important things in graphing. If you have any questions, be sure to write those down and ask me next class.